Good morning. In today's lecture, we'll discuss more about the negative numbers. So for the negative numbers, last lecture, I mentioned about the sign magnitude representation. And I mentioned there are some drawbacks for the sign magnitude. One of the drawbacks, two representations of the zero. And when you add and subtract positive with negative number, you will get a negative results, or you'll get false results in negative numbers. Therefore, there is another option to represent the negative numbers using something called complements. So the complements, it will be used for negative numbers representation. So in the complement, or the positive numbers will remain as is, as we know before, but the complements will be used only, or the what's there is the problem, which is on the negative representations. Before discussing how do we do the representations, there are two types of complements will be discussed. There are something called radix complements. Most likely we will focus on something called tens complements, which is tens complement. This will be associated with the decimal. And there are something called twos complement. This is associated with the binary. We will focus only in these two, binary and decimal. Most likely our main target is to focus on the binary, but I will discuss the decimal as a demonstration. So you can have, when you understand in decimal, you can understand in binary. Then the other type, which is there is something we call it dimension radix complement, or base minus one complements. In other words, or here when we discuss for base 10 in decimal, we will call it nines complement, like number nines complement. This will be used for decimal. And there will be one, which is for binary complements. Most likely, again, why it's called tens complement? Because decimal base 10, then 10. Why it is called nines complements? Because 10 minus 1, 9, this for the decimal. However, for the binary, the base is 2, then we have twos complement, we have ones complements. So all of this representation can be used to represent the negative numbers. So the negative numbers for decimal, it can be either in nines complement or tens complement. The negative numbers in the binary, it can be either twos complement or ones complement. So how we do the analysis on how we do the calculation for each one. So let's start with the dimension radix complement, which is most likely related to nines or ones complements. Let's forget about R, because R, it can be applied for any base system like octal or hexadecimal, but we don't want to go to this far. So let's focus only on nines complement or on tens complement. Most likely, we need to assume before applying the complements, we need to know how many bits do we have for each register. So in order to apply this complement, I cannot say I can apply it for any number. I need to make sure how many digits do we have, or how many for each register or for this device. Again, it's depending, for example, on the microprocessor. Sometimes the microprocessor can handle 8 bits. Sometimes can handle 6 bits, 4 bits, 7 bits, whatever. It can handle a certain amount. So we need to determine how many bits do we have. Otherwise, we cannot do the complements. So you need to keep this in mind. So let's assume that we have, like if we are assuming n bits, so we can basically say, for example, in nines complement 10 power n minus 1. Or the complements like if we can put n depending on the number of bits, then subtract it from the original number. How this formula being created? Most likely, we know like from idioms or like as identity, on plus off is on, right? Or we can say, for example, on, let me assume it. We can say another thing, a plus a bar will be 1. Or nuts, and a plus not a equal 1. Let's assume a is 0, then a is 0 plus not a is 1, it will be 1. Let's assume a is 1. which is going to be basically 1, plus not a, which is 0, will be 1. Okay? So the complement is the other half. So we can say, instead of to represent the negative number, we can say instead of the number is itself negative, we will find the complement, which is make the subtraction, or the opposite half, the other half, fill the other half. So, how can we find the complement for a decimal to find the ninth complement? The ninth complement will be 10 power number of digits minus 1 minus n. Let's assume we have a 6 bits. Here in this note, 6 bits. Sometimes, maybe in the quiz it can be 7 bits, 8 bits, or in the exam it can be 4 bits. So it's depending on what we will see. So let's assume that we have here 6 bits. So it will be 10 power 6 minus n. After that, 10 power 6 minus 1 minus n. I forget to mention. Minus 1, then minus n. That's how we calculated it. So 10 power 6 minus 1, in other words, you can write it as 9. So it will be 9, 9, 9, 9, 5 nines. 1, 2, 3, 4, 5, I think 6 nines minus 1, minus n, which is what we see here. So, how to find the complement of any number? Subtract each number from the nines. Then we can, let's assume that, like this example, we need to find the complement of this one. How to find the complement? Subtract 9 from all bits. So, how to subtract 999 from this one? 9 minus 0, 9. 9 minus 0, 9. 9 minus 7, 2. 9 minus 6, 3. 9 minus 4, 5. 9 minus 5, 4. So to find 9 complements, sometimes you don't need to like overdoing it like this way. You can subtract each bits from 9. So let's assume we have this number in decimal. 1, 1, 1, 1, 3, 4. Now this is in decimal. We need to find the 9th complements. What basically you need to do, look at each digit and try to subtract 9 from it. 4, 9 minus 4, 5, right? 3 minus 9, 6. 8 minus 9 minus 1, 8. 9 minus 1, 8. 9 minus 1, 8. 9 minus 1, 8. So this is 8, 8, 8, 8, 6, 5. Okay? That's how we find 9 complements. Clear? What's the point of doing this? We can say represents, for example, this is the number 1, 1, 1, 1, 3, 4, and we said the 9th complement is 8, 8, 8, 8, 6, 5. What's the point of this? We can say this is the negative number of it. And instead of putting a negative sign, we will represent this as this number. So we can get rid of the negative sign. That's the point of using the complements. Okay? It's the same way when we use it in binary, we add a digit called signed bits digits. Now we will not use a signed bit digits, we will use a complements just to put the negative sign. Now how about in binary? It will be the same as 10 power 6, for example. Here let's assume a 7 bits register. It's not 6, it's 7 bits. So here it will be 2 power 7 minus 1. 2 power 7 minus 1 minus the negative number, or the number which is n. In summary, it will be 1, 1, 1, 1, 1, 1 minus n. So how can we make the subtraction? Let's assume we need to calculate the complement of these parts. So you need to do subtraction. Subtract ones from each bits. 0 minus 1, 1. 1, I'm sorry, let's get 1 minus 0, 1. 1 minus 0, 1. 1 minus 0, 1. 1 minus 1, 0. 1 minus 1, 0. 1 minus 0, 1. 1 minus 1, 0. That's it. There is another shortcut that can be done instead of subtracting. Flip any 0, make it 1, any 1, make it 0. And that's it. So it will be much easier than doing the subtraction. Then, let's assume another example like 1, 0, 0, 1, 0, 0, 1. Then to find the two, it's called ones complements. Again, it's ones complement because in binary. So any 0 will be, any 1 will be 0, any 0 will be 1. So this will be 0, 1, 1, 0, 1, 1, 0. And that's it. Okay? So it's just like this simple. Just make sure to flip any numbers, any 0 make it 1, any 1 make it 0. So as a result, to find the 9's complements, any digit subtracted by 9, or 9 minus this digit, and to find the 1's complements, flip any 0 to be 1. Okay? So this again will be a representation of negative numbers using the 9's complement or using the 1's complement. So this is again make a great advantages to represent the negative number. So because the computer does not understand the negative sign. So we need to make sure how the computer will understand it. Again, the sign magnitude was not a good option because it will give us some false results, especially when there's positive and negative number. Then we need to use another representation using the complements. Okay. So, for example, let me assume we have 0, 0, 0, 1. This is equivalent to 1 in decimal, right? If I need to calculate or to make a number negative 1, using the sign magnitude, it used to be like 1, 0, 0, 1, right? Using the sign magnitude. But using 1's complements, it will be, this will be 0, 1, 1, 1. So this is representing negative 1. Like it will be like this. So you will see now the negative 1 representation using the 1's complement is totally different than using it in sign magnitude. So it's depending on their reference. So the positive numbers, they are all exactly the same as we used to be. So no change on it. But the representation using the sign magnitude or the 1's complement are different. So this number, when I look at this in the sign magnitude representation, this means negative, and here this is 2 plus 4, this will be 6, negative 6 actually, if you used the sign magnitude representation. Therefore, you should be aware of, so when you do the analysis, what's the code that I'm using? Am I using the code 1's complement? Am I using the 2's complement? Am I using the sign magnitude? So there are different codes that depending on like the software that you have or depending on the design that you have. So just keep in mind the 1's complement is totally different, totally separated than the sign magnitude. Please keep this in mind and don't get confused between them. So the 1's complements, here let me assume that we have 4 bits representation. Then we will see that the positive numbers, no change in the positive numbers. The only change occurred on the negative parts. So the negative parts, the complement of 0, 0, 0, 1 will be 1, 1, 1, 1, 0, as I showed you earlier. Then this happens for the remaining elements. So we can see that the positive 2, 0, 0, 1, 0, the negative 2, just flip them. It will be 1, 1, 0, 1. Right? How about, for example, the 7, positive 7, it is 0, 1, 1. Then make the complements will be 1, 0, 0. Just make the opposite. Flip any 0 by 1, any 1 by 0. So which is super straightforward. Clear? Now, the disadvantages of this one, we still have positive 0 and negative 0. Like 0, 0, 0, 0, and 1, 1, 1, 1, 1. So as we know, there is no negative for 0, no sign for the 0 is in neutral. Then for the 0, this means that we have 2 representations of 0. So this is one of the disadvantages using the ones complement. Sometimes it can create some problems with us. So even though that the ones complement is working fine, but there are still some challenges. Therefore, we need to look for another representation or some representation very similar to this, but can I get rid of two representations of 0? Yes, there is one representation. Using what? We call it radix complex, or using something called 2's complement or 10's complement. 10's complement for decimal, 2's complement for the binary. So in decimal, for the 2's complement as a result, so in the past, we used to say 2 power n minus 1 minus n. That's what it was in the 9's complements. Now, in the 10's complements, we will remove the 1. We will say 2 power n minus n. And that's it. 2 power n, sub n as number of digits. Let me fix it. Let me call it number of digits as n minus the number. So I just remove the 1. I didn't subtract 1. That's why I call it 10's complement. I keep it like 10 power 6 minus this number. Okay? Then the same for when we talked about 1's complement and 2's complements. 1's complement, it was 2 power n. Again, this will be small n. 2 power n minus 1 minus the number, but here it's 2 power n minus n. So the change here, we no longer can say 9 minus something to find the complement. This will make it harder. No, we cannot do it. This will be different. Or we cannot flip 0 by 1, 1 by 0. We need to apply the original formula, which is 10 power 6, for example, minus the number. Then it will take some time. So to find, let's assume we have 6 digits. So r power n minus n means 10 power 6 minus the number. So when we have this number, you need to put 10 power 6 minus this number. You need to subtract and make borrow and do this thing. So this will take some time to do it. For example, as I said, like here, 10 power 6 minus 54670. You need to make the borrow each one and do the analysis. Then for the binary representation, also you need to make it as binary. So 2 power n, 2 power 7, or in other words, it will be 10000 minus n. So this will take actually a lot of time by doing this analysis to do the 2's complement and the 10's complements. Is there any other easier way that we can find 2's and 10's complements? Yes. How? The 9's complement are basically, or the 10's complement are basically the 9's plus 1. And the same, 2's complement are basically the first complements plus 1, or the 1's complement plus 1. So how can I do that? The best way to deal with this, convert the number. For example, if you have the number in decimal, convert the number from 10's complement, from decimal to be in 9's complement. After that, add 1. So it will be much easier. So subtract 9's, then the final answer, don't forget to add 1. Then the same for the binary. Like when you have the numbers, there is the representation. Convert this to find the 1's complement, then add 1. Let's try to apply this. Will I get the same answer? Let me try it here. So this is, I'm going to write the number again here. 54670. Now try to subtract 9 from each part. Subtract 9. 9 minus 0, 9. 9 minus 0, 9. 9 minus 7, 2. 9 minus 6, 3. 9 minus 4, 5. 9 minus 5, 4. This is the 1's complements. The 9's. Then add 1. After adding 1, this will be 300. And this is 3, 5, 4. This is the 10's complements. So is this the same as the answer that we have here? Yes. Then this is the best way. Find the nines, then add 1. Okay? How about dealing with this number? We need to put this number. So we have 1, 0, 1, 1, 0, 0, 0, 3 zeros. So the best way, again, to deal with this, find the ones complement first, then do the second. So replace any 0 by 1, any 1 by 0. This will be 0, 1, 0, 0, 1, 1, 1. Then add 1. After adding 1, 1 plus 1, 10, 0 carry 1. Then 1 plus 1, 10, 0 carry 1. 1 plus 1, 10. Then here's 0, 0, 1, 0. And let me decorate it, removing this. And is this the same as this one? Yes. So this is the 2's complements. And that's it, straightforward. Now, it's no longer being that complicated, so you should be aware how to do it in like very few seconds. Okay? Any questions? So in summary, we have here 10s, which are basically 9s plus 1. How to find 9s? Subtract 9 each digits. For 2's complement is actually 1s plus 1. How to find 1s? Flip or replace 0 by 1 and vice versa. Okay? Let's summarize everything. Again, the advantage or why we are using this, because we need to make sure how to represent the negative numbers. All of the positive numbers will be the same, but here this is the complement how to represent the negative numbers. Let's look at this example. We have 623. We need to find the complements. How to find the 9's complement? Subtract 9 on each part. 3 minus 9, 6. 2 minus 9, 7. 6 minus 3, 3. Then this is 376. This is the 9's complement. In order to find the 10's complement, add 1. It will be 377. And that's it. Clear? Yes. How about this part? We have this binary. How to find the 1's complement? Replace any 0 by 1, any 1 by 0, so we will get this. To find the 2's complement, add 1. So this slide summarizes everything. The 2's complement representation, if we have 4 bits register, it will be based on this one. By making a comparison between this table and the previous one in the 2's complement, the positive numbers are the same. No change in the positive numbers. In the negative numbers, you will see we add 1 each, plus 1, plus 1, plus 1 each. So we would realize that in the 1's complement, this one 2's complements, we are representing a negative numbers in easy way. There will be no longer positive 0 and negative 0. There will be something or a new digit that we see here, negative 8s. So by using this representation, I can expand my range by including the negative 8s, which is making a great benefit on it. That's why now in real life, the computers, in order to represent the negative numbers, they are using the 2's complements. This is the standard. This is what's being used in real life now. To represent the negative numbers, we are using the 2's complements. So here, why I explained the previous complements. So as a demonstration, I will show you what are the challenges that we have. So you can see sometimes the sign magnitude can be used, but what dominates or what's being used is the 2's complements. So here I'm telling you like the overall story about it. So the 2's complements, which is the most important and the most efficient representation to represent the negative numbers, so we can handle it. But again, you need to keep in mind, you need to know how many bits do you have in this register. Otherwise, you cannot apply the complements. So in summary, I discussed about the something called dimension radix, which is based on r minus 1, which is 9's complement, 1's complement, and the disadvantages of it because we have two representations of 0. Then we discuss about the 10's complement and the 9's complement. I'm sorry, 10's complement and 2's complement, which are basically, they are only one representation of 0, and the other thing, I can expand my range by add another digit to my range. So, like for example, as I showed you in that table, -8 was included. Then it was fine. Then the problem can be good. Can be easier for us. So in order to represent any negative number, let me assume that you need to represent negative, like this, -100 as a binary. How can I represent this as a negative number? Using the sign magnitude, it can be represented as 1, 1, 0, 0. Using the 1's complements, I can represent it by flipping. It will be 1, 0, 1, 1. Using the 2's complements, it can be as add 1 to the 1's complement, so it will be 1, 1, 1, 0. Okay? Does this make sense? Yes.
The 2's complement, why would the third one be 1? When I go 1 plus 1 is 10, 1 plus 1 is 10, and then it'd be 1 plus 0 is 0.
Do you mean here? Just add 1. 1 plus 1, 10, 0, carry 1. 1 plus 1, 10. Oh, yes, you're right. I'm sorry. Thank you. Now, I want you to try these two examples. I want you to try 3, 4, 48. I want you to find the 9's complements and the 10's complements. The other scenario, like 41. I'm sorry, I can say 0, 11, 0. I want you to find this, to find the 1's complements and 2's complements. So try it now. Okay. What's the 9's complement?
651.
Let's see. So 8 minus 9, 9 minus 8, 1. 4, 9 minus 4, 5. 9 minus 3, 651. How about the 10's complements? 10's complements, just add 1, 652. How are the 1's complements? 1, 0, 0, 1. Straightforward. How about the 2's complement? Just add 1. This will make it 10, so it will be 10, 10. You see? That's simple. Now, this table summarizes like the 4 bits when n equal 4 bits register. Sometimes some number of bits can be 7, 6, 5, whatever. This is just a demonstration for 4 bits. You will see that the positive numbers, no change. The only change that we have in representing the negative numbers. So for the negative numbers, using the sign magnitude, just the same as the positive part, just put 1. Then we will realize that we have two representations of 0. Then using the ones complements, just replace 0 by 1, then we still have two representations of 0. The twos complements, we have only one representation of 0, and the other thing here, I can make it here, 0, 0, 0, 0. The other thing, which is, or the other important part, we have the 8s. Negative 8s is something new that can be added to my code just by using this code. I can expand my range. Then this is also another benefit. So my processor can handle or can work faster than others by using the twos complements because it can handle higher range. So that's why this is what's used in real life. Now, how can we use this in real life, actually? When we add positive numbers together, negative numbers together, it can be fine. But most likely, our concern when we do the subtraction, that was our problem. Or actually, the negative numbers comes, or the negative sign comes from the subtraction. How can we make the subtraction? Let's assume we have m minus n. So in summary, I can write it here because sometimes reading the notes here may be too complicated. So m minus n. I need to subtract this number. How can I deal with this problem? I'm going to solve it like m plus complements of n. Because I can represent the negative n as a complement number, as a negative number, minus n as a negative number. Okay? So minus n as a negative number, then if I find the complement, then it will be m plus n's complement, or the complement of number n. Now, what's the complement of number n? It's depending on the which code I'm using. And of course, what's the representation? Am I using decimal or binary, and also depending on the representation. So in summary, when you have m minus n, we have two scenarios. Let me write it here. We have two scenarios, or two options, doesn't matter. So the first thing we can observe, m larger than n. And the second option, when m less than n. How can we deal with this problem? When m larger than n, this means this is positive number. Right? The answer must be positive. Positive answer. Do you agree with me? Yes. I'm trying to fix my writing. I'm sorry. Positive answer. When m less than n, this means negative answer. How can we treat this? When we have a negative answer, to represent the number back to the origin, take the complements of final answer and put the negative sign. But when we have m larger than n, most likely we will have something we call it carry out bits. So when we have a carry out bits, it depending on if we are using nines complement or ones complement, or if we have ones complement or tens complements or twos. So the carry out bits, if we are dealing with nines complement and first complements, this will be, or ones complement, this will be add the carry out bits to the final answer. If we have tens complements and twos complement, the carry out bit will be ignored. How? Let me summarize these notes, and we will apply some examples. I'm going to summarize it like this way. Nines complements, ones complements. Again, we can have m larger than n. What we will do, add carry out bits to first bits. And when we have m less than n, here that was positive answer, here is negative answer. Here, don't forget to take the complement of the final answer. While when we want to discuss about 2's complements and 10's complements, the scenario is m larger than n when it is positive. What we will do is ignore carry out bits. Then the other option, when it is negative, which is the same that I discussed here, which is take the complements of the final answer. When you realize or know the answer will be negative number, of course, don't forget to take the complements. But when you realize during your analysis that the number is positive, look at the carry bits. This is one of the common mistakes or one of the tricky points, which is look at the carry. Am I dealing with 2's complements? Then ignore the carry. If you are dealing with 1's complement or 9's complement, then include the carry at the first bits. Let's see an example so it can be much easier. Here we are subtracting using the 9's complement. The general solution, let's assume here in the 9's complement we have 841 minus negative 3029. How we deal with this? Regular subtraction if we need to use the general subtraction. 1 minus 9, you need to take a carry out, so it will be 11 minus 9, this will be 2, then 8 minus 2, 3 minus 2 will be 2, then 8 minus 3 will be 5. So I think, yeah, 522, right? Or no, because we take a carry out. We borrow. Oh, even subtraction, I cannot do it. 9, this will be 3, this will be 11, 11 minus 9, this will be 2, this will be 1, 512. Okay, 512. Now, how to do this using the 9's complements? To find the 9's complement, subtract 9 on each digit. So 9 minus 9, 0. 9 minus 2, 7. 9 minus 3, 6. Right? You agree? Then, let's do the addition. 1 plus 0, 1. 4 plus 7, 11. 1 plus 8, 9 plus 6, 15, right? Don't write it like this way. This is incorrect. Why? Because we have a carry out bits. Remember, or in this one, we have only 3 bits. The system or the computer can handle only 3 bits. It can handle 1, 2, 3. What will happen to this? This is called carry outs, which is out of range. My computer can handle only 3 bits. And this bit is out of range. What should I do with it? Add it here. So it will be 1, 5. Here, the remaining, what this question will be? It will be 5, 1, 1. Take this 3. Then plus add the carry bits. So it will be 512. Now, did I get the same answer here? Yes. Okay? Clear? Okay, let me choose another example. I'm going to assume it's the same as 3 bits. So 990 subtract 200. So basically, using the general math, it will be 790, right? Now, how about using the complements? So 990 plus 9 minus 0, 9. 9 minus 0, 9. 9 minus 2, 7. So it will be 0 plus 9, 9. 9 plus 9, 18. 1, 19, 10 plus 17, 7, and there's a carry out bit 1, right? So this carry out bit will go here, so plus 1. So it will be 789 plus 1, 790, which is the same as this one. Okay? Yes?
Could you go to the previous slide?
Do you mean
Not now.
here?
Yeah, just those notes.
Yes.
Appreciate it.
You can have the recording, you can see the recording in case if you need to go back to it in the future. So basically, take the complements. That's how we do the subtraction. That's how the computer doing the subtraction actually. Any questions? Okay, let's go to the other. So how about if we do this subtraction, which is 841 minus 983. We can realize that the negative number is larger than the positive. So the answer, of course, must be negative. After doing the subtraction, it will be negative 142, right? How can we do it? Using the ninth complements. Using the ninth complement, replace 9 minus 3, 6. 9 minus 8, 1. 9 minus 9, 0. So 841 plus 0, 16. So 1 plus 6, 7. 4 plus 1, 5. 8 plus 0, 8. There is no carry bits. Then that's fine. But you see, the answer is 857. This is not the number negative 142. Yes, this is not because we haven't converted this. Yes, we haven't added yet the negative sign. How to add the negative sign? Find the complement of these parts. Remember the rule here I mentioned. If it's negative, take the complements of the final answer and put the negative sign. So what should I do? Take the complement of this number. 9 minus 7, 2. 9 minus 5, 4. 9 minus 8, 1. Put negative sign. Is this the same as this one? Yes. Then problem done. Clear? Another example. Let's assume we have 505 minus 600. 505 minus 600, negative 95, right? And don't forget here, because we have a 3-bit register, put 0. Don't forget. We must be consistent with the number of digits. Even if it's 0, make it like this. Now, how we can find this using the complements? Using the complements, it will be here. 505. 9 minus 6, 9. 9 minus 6, 9. 9 minus 0, 9. 9 minus 0, 9. 9 minus 6, 3. So it will be like this. So 505 plus 399. So the answer will be 5 plus 9, 14. This will make it 10. So this is 0. Then will be carry out 1 plus 5, 6 plus 3, 9. Is this correct? Okay, 5. Yes, that's correct. Now, we know that the answer must be negative. So, we need to find the complements. To find the complements, 9 minus 4, 5. 9 minus 0, 9. 9 minus 9, 0. Put a negative sign. Is this the same? Yes. Then that's it. Any questions? Okay. Now, how can we apply this for the tens complements? Now, we applied here for the nines. In the tens complement, it will be exactly the same procedure, but keep in mind when there is any carry out bits, ignore it. Don't add it to the first bit like what we did here. here we add it to the first bits. Don't do it. This is if it is in tens complements. Here's the tens complements. 325 minus 641. So the answer should be negative 316. How do we do it? Using the complements. Don't forget we are doing tens complement. Don't say like 9 minus 1, 8. 9 minus 4, 5. 9 minus 3, 9 minus 6, 3. Then don't write it 358. Don't forget there is 1 has been added. Right? Because this is the 9s. This is plus 1 equal to 10s. Right? So 359. Again, one of the mistakes, some people just find the 9s. Remember, this is tens complements. So find the tens. Okay? Then we have 325 plus 329. So 5 plus 9 will be 14. 4 carry 1. 1 plus 3 plus 2, 3 plus 5, 8. 3 plus 3, 6. There is no carry bits. 384. No carry bits. Okay, everything's fine. But remember, the negative parts is larger than the positive parts. So what should I do? Do the complement and add the negative sign. So let's put a negative sign here, and let's do the complements again of these parts. The complement of 4, 4 minus 9, 5. The complements of 8, 8 minus 9 minus 8, 1. The complement of 6, 6 minus 9 minus 6, 3. But remember, this is the 9s. Don't forget to add 1. So it will be 316 negative. So the confusing parts about maybe doing the tens complement is sometimes you will forget adding 1 when, but just be consistent. Remember, this is tens complements. If you know how to do the transformation very well, then that's all right. And when there's any carry out bits, ignore it. So this is the confusing part, and there will be a quiz in Friday, so you will see some of this in the quiz. Two's complement, nice complement, and this conversion. Okay? And of course, you need to know how to make the conversion between binary to decimal, to hexadecimal, to octal, and the tables that's most likely it will be provided. You don't need to memorize the table of the hexadecimal or memorize the table of the octal. So you need to know how to make the conversion, any number, to hexadecimal, to binary, to octal, and you need to know how to make also the addition, subtraction, multiplication, and division. Okay, now let me pause and take a 10. Okay, yeah. Okay, so now how about if there is a carry out bit like this? 821 minus 413. So the answer basically must be negative. Will be positive. 408. How can we find this? Find the nice complement for this number first. So 3 minus 9, 6. 8 minus 9 minus 1, 8. 4 minus 9, 9 minus 4, which will be 5, then add 1. So it will be, I think there's a typo mistake, this should be 587, okay? Then do the addition. 1 plus 7, 8. 2 plus 8, 10, 0 carry 1. 1 plus 8, 9, plus 5, 14. This is a 3 bits, so we have a carry out bit 1. Do we need to add it here and say plus? No. So that's it, 408. And it's positive number, so we will ignore. This is the trick of the, or this is the point when we deal with tens complements, we need to ignore it. Ignore the carry out bits. Any questions? Okay, how about using 1's complement and 2's complement like this? We need to subtract 1101 from negative 1, 0, 0, 0, 1. How to do this subtraction? Using the complements. Let's use the ones complement here. In ones complement is the same scenario that we apply in nines and tens, but we will apply here in ones. So it's basically 1. It is 1, 1, 0, 1, minus 1, 0, 0, 1. We can find the ones complement for this part. It will be 1, 1, 0, 1. The ones complement will make it positive, so it will be 0, 1, 1, 0. Do you agree with me on this? Okay. So when you add the addition, 1 plus 1, 0, will be 1. And 1, 0 plus 1 will be 1. 1 plus 1, 0, carry 1. 1 plus 1 will be 0, and there is a carry out 1. Remember, how many bits do we have here? This is 4 bits. So we have a carry outs. What should I do with the carry outs? Since we are in ones complements, you will add it here. So it will be 1 plus 1, 10, 0, carry out 1. Then 1 plus 1, 10, 0, carry out 1. Then it will be like this. So this is the final answer. So why I explained nice complement and tens complement, because nice complement and tens complement, it's easy to demonstrate, easy to understand. But when you apply it here, if you forget the carry out bits, sometimes you will not realize this. You will fall in the trick without realizing this. So if you know how to do it in nice complement, you will do it in ones complement. If you know how to do it in tens, you will do it in twos. Okay? So here, because there's a carry out, then it matters. Then you need to consider it. How to double check our answer? Actually, 1101 is equivalent to 13. 10001 is equivalent to 9. 13 minus 9 will be 4. Now, is this number 4? Try to convert this number to binary. This will be 0 times 2 power 3 plus 1 times 2 power 2 plus 0 times 2 power 1 plus 0 times 2 power 0. Then the answer will be 0 plus 4 plus 0 plus 0, which is equal to 4. Then our answer is correct. That's how we check it. Most likely in the quiz, maybe you will see validate your answer. Then the way that you validate your answer, you can convert both in decimal, make the subtraction, and your final answer that you got in the binary, convert to decimal, then you will say they are both correct. Okay, because you will see it in the quiz. Now, how about when we make this subtraction? So 1101 minus 1110. So we realize this number, this is m, this is n. N is larger than m. So how we do the calculation? The same as normal. So it is here 1101. Now it's subtract 1110, but we need to find the complements. So it will be 1101. Do the complement for this part, which will be 0001. Then make the addition. So the answer will be 1 plus 1, 11. 1 carry out 1. So 1 plus 0, 1, 1, 1. So by looking at this answer, let me double check. Yes, 1, 1, 1, 1. Did I miss something here? Yeah, there should be 0. Yes.
Yeah.
Thank you. Now there is no carry out bits. So this is the number, but this is the number is written into the 2's complement representation. So I mean, on the 1's complement represent in the complement representation, but in order to add the negative sign, you need to convert this number and to take it. If you need to find it in negative parts, you can find it, which is basically find the 1's complement of this part. It will be, this number is equivalent to negative 0001. If you need to calculate it in negative. If you need to keep it like this, it can be done. It can be fine. Okay? So this number If you need to add the sign, how we understand the negative parts. Double check our answers. This is 1110, 13, 11110, 14. 13 minus 14, negative 1. And this is what we get here. Okay? Any questions? Now, how about using 2's complement? Again, this is the most commonly used in real life, which is 2's complements. Okay, how to deal with this? Remember, in 2's complements, ignore carryouts. Keep this in mind. Then it will be fine. So we have 1101 minus 110001. So basically, it will be as 1101 plus find the complements. How to find the complement? Find the ones first, then plus 1. The ones first complement, it will be 100. I missed it. It will be 1 will be 0, 0 will be 1, 0 will be 1, 1 will be 0, plus 1. So it will be 1101 plus 0111. Do you agree with me in this? Okay, so let me write it like this: 1101 plus 0, 0111. 1 plus 1, 10, 0 carry 1. 1 plus 0 plus 1, 10, 0 carry 1. 1 plus 1, 10, plus 1, 11, carry 1. 1 plus 1, 10, 0. Remember, it's 4 bits, so we have a carry out bit 1. What we will do, ignore. So the answer will be 0, 1, 0, 0. Validate your answer. This is equivalent to 13. This is equivalent to 9. 13 minus 9, 4. And when you convert this, it will be 4 in decimal. Okay? Straightforward. Just keep in mind that when you convert, find the 2's complements, find the ones and plus 1. Yes?
Where did you get 0110?
0, 1.
10, yeah.
Find the 9's complement or the 1's complement of this one. Convert every 1 by 0, every 0 by 1.
Oh.
Then add 1 because again we are in 2's complement. Yes?
Did you say that the 2's complement is the only one that you ignore the carryout bit, or is there another one that also ignores it?
Which is the 10's complement as well.
Okay.
2's and 10's. Yeah. Because those are what call it radix representation, and the other one 1's and 9's with the diminished radix. Or we call it R minus 1 or R. So 10 with decimal, 2's with binary, which is with the base 10, base 2, then ignore the carry bits. But 9's and 1's, which is the base minus 1. Then here the carry bit will be added to the first bit. Okay? Another case study, which is when we have 1101 minus 01110. How to deal with this? 1101 plus find the 1's complement first, then add 1. So 1 here will be 0. This one will be 0, this one will, the third one will be 0, the fourth one, the first 0, or the fourth digit will be 1, then plus 1. Again, we add plus 1 because we need to convert to the 2's, not to the 1's. So it will be 1101 plus 0, 0, 10, because 1 plus 1 will be 10. How to do it? 1101 plus 0010. 1 plus 1, 1. 1 plus 0, 1. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, 1. Remember, this is m, this is n. Here in this case, m less than n, so the answer must be negative. So, if we need to add the negative sign, in case if you need to calculate, add it, it will be negative. Do the complements, 0, 0, 0, 0, then add 1. So it will be negative 0, 0, 0, 1. Why we did this? Because this is the 1's plus 1. Do the complements. Now, validate the answer. This is 13, this is 14. 13 minus 14, negative 1. Okay? It looks like tricky, but please try to practice more at home, because this will be again, the topic of the next quiz, which is on Friday. So please make sure to study like very well on it and to practice more. Let's see these examples. And let's see, can we handle it? These examples will be in 2's complements. That's most likely what the computer doing. So 5 bits register, 10101 minus 00111. The first observation you need to keep in mind, which type of registers do I have? 5 bits registers? Okay, 5 bits registers, and that's. So what should I do? It's m minus n, so we realize that m is larger than n, then the answer must be positive. How to deal with this? Using the 2's complements. So basically it will be 10101 plus find the 1's complement, then add 1. So it will be 1100, 3 zeros plus 1. I guess now you are familiar why I did this. Then it will be like 10101 plus 11001, like this way. So 1 plus 1, 10, 0 carry out 1, 1 plus 0 plus 0, 1, 1 plus 1, 1, 1 plus 0, 1, 0 plus 1, 1, 1 plus 1, 1. Remember, it's 5 bits register, so we have a carry out bits. So ignore, because we are in 2's complements. So the final answer will be, I think 1 plus 1, this is 0. I apologize. The final answer will be 01110. Why this is 0? Because 1 plus 1 will be 10. I don't know why I put it. Okay? So this is the final answer. How can we validate this? You can convert any number to binary or convert this number. We will realize that this number is 27, this number is 7, so 27 minus 7 will be 14. Try to convert this, it will be 14 to binary. That's how we validate your answer. Let's see another example. This is your turn. Try it and please let me know. Do the subtraction. 10101, which is basically 21, minus 23, the answer must be negative 2. So how can you do it? The first step, or you need to keep in mind that the n is larger, m is less than n. Then what you need to do, find the complements first. How to find the complements? This is 10101 plus find the 1's complement and add 1. Replace any 0 by 1 and any 1 by 0, then plus 1. So it can be 10101 plus 01001. Then do this addition. And remember, the final answer must be negative. Then don't forget to do the complement for the final answer if it is needed. So how can we make this addition? One plus 1, 10, 0 carry out 1, 1 plus 0 plus 1, 1 plus 0, 1, here is 1, and here is 1. The final answer must be negative, so do the complements. When you do the complement, it will be 0, 0, 0, 0, 1 plus 1, because 1's plus complement plus 1. So it will be 0, 0, 0, 10. And don't forget to put the negative sign. This is in case if you need to calculate it as a negative sign. Okay? So this is equivalent when you converted it to decimal, it will be negative 2. And that's what we have. 21 minus 23, negative 2. No. Let's do this. Let's assume this example we have. Let me see if there is another more example. Yeah, we do have more. Okay, we have 100 minus 37, and let's assume we have 8 bits register. 8 bits binary register. We need to find this using the 2's complements, not using the 9's or 10's. What should I do? Convert all of these numbers to binary first, then do the analysis. So what we need to do, convert the 100 to binary, and keep in mind, after converting this to binary, it must be 8 digits, 8 bits. So when you convert this into binary, you will realize it will be 1100100. But count them, 1, 2, 3, 4, 5, 6, 7. So you need to add 1 more bits to make it 8. Again, we are with 8 bits register. Okay, do you agree? So, how about the other number? The other number here we have 37. 37, you need to convert this to binary. After converting this to binary, it will be 100101, but complete the number of bits to be zeros, to make it 8s. 1, 2, 3, 4, 5, 6 bits, so add 2 zeros, so you can make it 8 bits. Remember, we need to make it 8 bits. 8 bits. This is what the question mentioned. Okay, so far so good? Now, we need to do the subtraction. In order to do the subtraction, we need to represent the negative 37. How to represent the negative 37 in binary using the 2's complements. Basically, find the 1's complement for this number first, then do the 2's complement, then add 1. So replace any 0 by 1, any 1 by 0. It will be 1, 1, 0, 1, 1, 0, 1, 0, plus 1. Do you agree? Then substitute the number. It will be 1, 1, 0, 1, 1, 0, 1, 1. This is the negative 37 in this representation. Now, I'm ready to do the subtraction. I can say 100 plus negative 37, which is equivalent to here 0, 1, 1, 0, 0, 1, 0, 0. This is equivalent to 1, 1, 0, 1, 1, 0, 1, 1. Then do the addition. 0 plus 1, 1. 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 1 plus 1, 10. 0 carry out 1. 1 plus 1, 10. 0 carry out 1. Since we are in 2's complement, ignore carry. So the answer will be 0, 0, 1, 1, 1, 1, 1, 1. This is in binary. And since the number must be positive, then that's it. You didn't do the complements. Validate the answer. 100 minus 37, it is 36. Now, if the question says validate your answer, convert this to binary, from binary to decimal, it should be 36. It must be 36. Then we can say our answer is correct. So, okay, this is clear? Let's see another example. 12 minus 5 or 5 minus 12. Let's try these two. And I'm going to assume we have 4 bits. And the word 4 bits is very important. So how to represent the 12, how to represent the 5. So 12 can be represented as 1, 1, 0, 0 in binary. 5 can be represented as, in 4 bits, it will be 0, 1, 0, 1. Now, how to represent the negative 5? The negative 5, do the complements, which will be, do the ones first. It will be 1, 0, 1, 0 plus 1. which is going to be 1, 0, 11, like this. How to represent the negative 12? Do the complement first, which will be 0, 0, 1, 1, plus 1. Then it's going to be 0, 1, 0, 0, 0. I think 0, 1, here 0, 0, 1, 1, so it will be, 0, 1, 0, 0. Okay, now do you agree with me how to represent all of these numbers? Now let's do the subtraction. Let's make 12 plus negative 5. 12 is equivalent to 1, 1, 0, 0. Negative 5 is equivalent to 1, 0, 1, 1. So 0 plus 1, 1, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 10, 0 carry out 1, ignore the carry. So the answer will be 0, 1, 1, 1 in binary. And when you convert this, it will be equivalent to 7 in decimal. And that's what we used to, that's normal. So 12 minus 5, 7. Okay? How about the opposite? 5 minus 12. So 5 is equivalent to 0, 1, 0, 1. Negative 12, we found here 0, 1, 0, 0. So 5 minus 12, it must be negative 7. So 1 plus 0, 1, 0 plus 0, 0, 1 plus 0, 1 plus 1, 10, 0 carry out 1, then it will be 1, 0, 0, 1. This number, you need to find the complements because it must be negative number. So how to find the complements? So to find the complements, put a negative sign here. It will be 0, 1, 1, 0, plus 1, then it will be negative 0, 1, 1, 1 as a binary. And when you convert this, it will be negative 7 as decimal. Okay? So all of these techniques that I'm discussing here is because of the negative numbers. The computer does not understand the negative, so how can we make the computer understanding this? Okay, so here, the sign magnitude, the 2's complement, 1's complement in this table, using different representations, using the, I think, 4 or 5 bits register. It's the same as I showed you earlier. Then next lecture we will continue from here. Any questions about these examples? Okay, please make sure to study very well for them. You can try, for example, at home. How about if 10 minus 5, 5 minus 10, like similar to this example, and see how we can handle it. So this example is very important. Thank you.